Today we're going to look at resonant current balancing from a 4-to-1 1 kVA transformer, which is going to go to a load, a ferrite load, and we're going to heat that ferrite up to incandescence by virtue of its nonlinear load. The resistance of the ferrite itself is dependent upon the voltage induced on it. To backtrack on the entire method here, what I'm calling resonant current ballasting, is we're going to look up. First of all, we'll describe the situation in the circuit as is before we hook the ferrite load to it. Right now the variac's set at 12 volts just to show the proportions. We got an input amperage of 4.2 amps at 8.9 volts. In the combination of this resonant system of 25 millihenry coils, we have an input of 8.9 volts, whereby the transformer primary is placed inside the tank circuit, resulting in 143.5 volts out. So as we can see in this method, ordinarily we would only be getting 40 volts out on a 4-to-1 ratio, 10 volts input output, but now we're getting 140. So first, now then, we want to go back and look at the parameters of the initial circuit, in which I've drawn a diagram up here. I call this the binary resonant tank. Opposite reactances share common pathway on midpoint pathway, leading to unity of reactive currents. As one can see here, we have L1 and L2 being connected in a form of a S, and the same thing with the capacitive circuit. But on the midpoint path, we have unity of reactive currents. And what that means is that we can, what we will do now is to demonstrate that, we will short out the primary. And when we short out this primary, it will be the same circuit as described in this schematic above. Now we have an input of 0.3 amps at 10.8 volts. It's splitting on one side at 0.50 amps, 0.64 amps on the other side, and on the midpoint amperage, which is the unity of those reactive currents, we have 1.13 amps. Now we see that since when we added the transformer, this dropped down to 0.55 amps, that we would think that we probably would have maximum energy transfer between the resonant circuit to the ferromagnetic circuit by virtue of the fact that the amperage was halved. Okay, now we want to try to quickly show the tuning involved in how the circuit is actually tuned. And to do that, we're going to shut one side. We're going to shut one side down. First of all, we're going to shut off. First of all, we're going to shut off our midpoint amperage. Note the conditions and the rise of the circuit. When we disconnect the midpoint amperage line, it will now be two inversely phased series resonances, exactly as the diagram shows. If we put an X there and eliminated that midpoint path, we have L1, C1, and we also have C2, L2, and these are constructed in opposite manners with the sources of connection. Therefore, they are inversely series resonances, inversely made series resonances. Now quickly, we just want to show that in fact the circuit is at its maximum resonance. First, we'll disconnect the midpoint amperage line and show what the circuit consumes in that instance. We got 2.4 and 2 amps on the respective sides. Complications evolve from the fact that this entire system here is sitting on top of the similar made system using high induction coils. And them high induction coils themselves produce amperage, generally 6 milliamps is considered 120 volt level. And so we can see here, this step-up transformer is producing probably about 100 volts on each coil, and we're only inputting 8.7 volts at this time. This portion of the circuit we're not going to worry about right now, but we're just going to demonstrate what the top circuit does. So now then we have the two resonances. We're going to make a further modification. Need a wire. Need a wire, excuse me. And a calculator. We're going to make a quick test for resonance. And we're going to shut one side down and just test one side specifically. So we'll shut the front side down. Notice how the amperage on shutting the front side down, that should change once we disconnect that portion. It's gone up a little bit. First, we're going to short out the coil. This is going to tell us our capacitive reactance. Our capacitive reactance shows itself to be 10.9 volts, enabling 1.17 amps, coming out to 9.31 ohms. Now we're going to short out the other side, carefully to note that we want to make sure that we never apply both shorts on both sides, otherwise, see the bulb is lighting up. That's the air core transformer aspect. That's got the amperage has gone back up on one side. We can see that the secondary is procuring high voltage, and that's demonstrable just visually. Now we're going to go back and we're going to short out the capacitive bank in this instance to see our inductive reactance on that coil. And now we have 10.6 volts enabling 1.14 amps, and that gives us 9.29 ohms. So we have 9.31 ohms versus 9.29 ohms. So we're fairly close on resonance. That's demonstrable. But now here's where the peculiar thing comes in. Right now we're looking at the inductive reactance. We're looking at the fact that the secondary is producing high voltage, and we will assume then that this reactance must be changed by the presence of the outer coils. Yet it does not change. If it would change, the 114 went down to 112. Not much of a significant change for the amount of mutual inductance being observed. We'll put that back. That means that these things can be tuned approximately, even though there's loads on them, as if they were in isolation. Now we're going to remove the short and show one more thing. And we're getting close to the end here. Oh, goodness gracious. Christ. And we'll assume that went there. Okay, we're going to remove the short. Where was the short? Here's the short. Okay, now we're back. God damn it. Now we're back to our preliminary situation. We got wire problems. It looks like we're going to call that the end of this video. Thanks.